Hey Math Journey! Today, we've got a wild expression to demonstrate the astonishing power of geometry in solving some challenging algebra problems. Let's dive in. The expression is square root of 58 minus 42 times square root of x plus square root of 149 minus 140 times square root of 1 minus x. The question asks us to find the smallest possible value of this expression when x is a real number within its domain. Let's start by finding the domain of the expression. Since there are square roots, the values inside them must be non-negative. 58 minus 42 times square root of x greater than or equal to 0, and 149 minus 140 times square root of 1 minus x greater than or equal to 0. From the first inequality, we get x less than or equal to 58 over 42, and from the second, square root of 1 minus x less than or equal to 149 over 140. Since square roots are naturally limited to values between 0 and 1, it follows that x must lie within the interval. Thus, the domain of the expression is as this. At first glance, this expression looks complicated, but let's take a closer look at the numbers involved. Could there be a hidden structure? Notice something interesting. The numbers 58, 42, 149, and 140 may seem random, but they actually follow a pattern. 58 is 7 squared plus 3 squared. 42 is 2 times 7 times 3. 149 is 10 squared plus 7 squared. 140 is 2 times 10 times 7. See the connection? These numbers are hiding a geometric trick. Let's uncover it. If you've ever struggled with algebraic simplifications, let me know in the comments. This part is going to blow your mind. Instead of wrestling with complicated algebra, let's take a different approach: geometry. We can rewrite our radicals using the law of cosines from trigonometry. It states, c squared equals a squared plus b squared minus 2 times a times b times cosine of theta. This means our problem actually describes the sides of a triangle. By leveraging this, we can simplify our expression in a way that reveals its minimum value much more easily. Now, let's set square root of x equal to cosine of theta. That way, we turn the problem into something more manageable. Why cosine of theta? Because it naturally stays between -1 and 1, which is perfect for our square roots. Since x is between 0 and 1, the square of x also falls within this range. Consequently, theta must be between 0 and 90 degrees. Similarly, we can set square root of 1 minus x equal to sine of theta. And since sine and cosine are complementary functions, we can rewrite sine of theta as cosine of 90 degrees minus theta. This substitution helps us express everything neatly in terms of cosine, making the problem even easier to handle. So, the function can be rewritten as f of x equal square root of 7 squared plus 3 squared minus 2 times 7 times 3 times cosine of theta, plus square root of 10 squared plus 7 squared minus 2 times 10 times 7 times cosine of 90 degrees minus theta. This means our problem actually describes the sides of a triangle. Imagine a triangle where two sides are 3 and 7, with an angle of theta between them. The missing side? That's exactly what the first square root term represents. Similarly, the second radical follows the same idea, this time, with a triangle that has sides 7 and 10. But here's the cool part: the angle between them is 90 degrees minus theta. And this is the part where math magic happens. We now understand as the sum of two missing triangle sides, BD and DC. But here's the key insight: instead of treating BD and DC separately, let's think about their total length in the overall structure of the triangles. The shortest possible sum happens when BD plus DC aligns perfectly with a single straight line, specifically, the diagonal BC, which directly connects the endpoints. What does this mean? It means that the minimum value of f of x is simply the length of BC, the diagonal of a right triangle formed by sides 3 and 10. In other words, rather than computing each radical separately, we recognize that their minimum sum is just the hypotenuse of a triangle with sides 3 and 10. To find the minimum sum, we use the Pythagorean theorem. We take the square of 3 and add it to the square of 10. 3 squared plus 10 squared equals 9 plus 100. Now, we take the square root of this sum. The square root of 109. So, the minimum value of f of x is the square root of 109. And there you have it. We managed to solve this challenging algebra problem using the power of geometry. If you enjoyed this challenge, don't forget to hit that like button and subscribe to Math Journey for more fun math adventures. Now that you've seen the answer, how did you do? Were you able to crack it? Let me know in the comments. And share this video with a friend who loves brain teasers to see if they can solve it without peeking at the solution.